Now let's talk about inverse functions. So here I have a function f with three ordered pairs. We say that f and g is another function, are inverses of each other if the domain of f is the range of g and the range of f is the domain of g. What it means is x and y will be swapped. So for g, the order pairs will be 80, 100 instead of 100 and then 80 like in f. And then this next one will be 120 as the x coordinate and then 150 as the y coordinate. And finally, this will be 160 for x and 200 for y. So we call f and g are inverses of each other. So here's a formal definition. Let f be a one-to-one function. Then function g, which is the inverse of f, and the notation for the inverse function of f is f and then with what looks like an exponent of -1, but it does not mean 1 over f, okay? It's just the notation for inverse. So f -1 is the inverse of f if the following are both true. First, if you compose the two functions that are inverses of each other, then you get x. Let me recall that when you have f and then the little o in between, and then f of -1, this translates to f of f -1 of x, composition of two functions. Okay, and the second condition is if we reverse the roles of the two functions. So initially in the first one, f is the outside function and f -1 is the inside function. And then the second condition, f -1 would be the outside function, and then f would be the inside function. So this could be translated to f -1 of f of x. If we perform this composition of these two, we also get x. So you have to get x in both scenarios for them to be inverses of each other. So let's look at this example. Determine whether the functions are inverses. So f of x is equal to 100 plus 12x. And g of x is x minus 100 over 12. So check the first condition. The first condition, we have to compose the two functions with say f on the outside and g on the inside. F is determined by 100 plus 12 times x, but instead of x, we want g of x here. So that means 100 plus 12. Now g of x is defined by x minus 100 over 12. Okay, so this is multiplication. Simplify this expression. 12 and 12 cancel. So you are left with 100 plus x minus 100. And 100 and minus 100 cancel, give you 0. So you end up with x. So it satisfied the first condition. Now, second condition, we want to compose the two functions, but this time g will be the outside function and f will be the inside function. G is defined by x minus 100 over 12. So instead of x, we want f of x to be the input, minus 100 over 12. F of x is defined by 100 plus 12x. And then, so that's for this one. And then I have to bring over the minus 100. So minus 100 here. And then all over 12. In the numerator, 100 minus 100 gives you 0. So you're left with 12x divided by 12. 12 and 12 cancel, give you 1. So you're left with x. So in both cases, we show that the composition of two functions both equal to x, whether a function's on the inside or outside. And because we were able to show both conditions, we can conclude that yes, f and g, f of x and g of x are inverses of each other. Okay, next example. Here we have h of x is equal to cube root of x minus 1, and k of x is equal to negative 1 plus x cubed. So let's check the first condition where you compose the 2 with, say, h on the outside and k on the inside first. So h is determined by cube root of x minus 1, and instead of x, I want k of x to be the input, minus 1. And k of x is defined by negative 1 plus x cubed, so let's just substitute that in for the k of x here, and then bring over this minus 1. Simplify this. This will give me x cubed minus 2. This cannot be reduced to x in any way, so it failed the first condition, and therefore we can conclude that is they are not inverses of each other. So h and k are not inverses of each other. It is recommended that you do these steps here to double check if two functions are inverses of each other in problems where you have to find the inverse function. So after you find the inverse function, you should be able to check to see if your answer is correct by checking these two conditions.